Yep. You may
Yeah,
start. Yep.
okay. And hello, everyone. I'm Conway from Aura. And today, I'm going to introduce our latest research, OPML, Optimistic Machine Learning. Before we started, we are going to talk about the proving system in the blockchain. Currently, there are two types of popular proving systems. One is ZK proof, another is a fraud proof. And many people may heard about the rollup system. And indeed, correspondingly, there are two types of rollup system. One is the ZK rollup, which will utilizes the zero-knowledge proof to guarantee a security, such as the Stuxnet and ZK-Sync. Another type of the rollup system is the optimistic rollup, also known as OP rollup, such as Arbitrum and Optimism. And for the proof type perspective, the ZK proof can prove something correct, but the fraud proof adopt a totally different approach. The fraud proof cannot prove something correct, but it can only prove something is incorrect. Therefore, in the fraud proof system, people often directly upload the result on chain and optimistically consider the submitted result is correct. And there always exists a challenge period, and we're waiting for other validator to check the result. And the cost of generating a ZK proof is extremely high due to the cryptographic limitation, but the cost of generating the fraud proof is extremely low. And here is a page that I collect from the layer 2 bit. And we can find that most of the layer 2 blockchain adopt the optimistic rollup. This is because the fraud proof system is indeed much cheaper than the ZK proof, and the fraud proof system is much more mature. And when coming back to the on-chain AI, many people may have heard about the ZKML, which will adopt the ZK proof to bring the AI result on-chain and guarantee its correctness. And we're wondering that why not adopt the fraud system to make AI on-chain? With that idea in mind, we have proposed OPML. And we have released the paper OPML, Optimistic Machine Learning on Blockchain, on arXiv. And if you are interested in it, feel free to explore our white paper and repo. Coming back to the on-chain AI, we know that in ZKML, we need to convert an AI model to ZKML model, and we need a ZK prover to generate ZK proof for the AI model inference. And then we'll send the ZK proof back to the on-chain verifier contract to check the ZK proof. Indeed, the main limitation of ZKML is that the cost of generating a ZK proof is extremely high. But in OPML, we do not need to generate a ZK proof. Instead, we'll first convert an AI model to the OPML model, and then we can conduct the execution of OPML model off-chain in a native environment, and then directly upload the result on-chain. And optimistically, we'll consider that the submitted result is correct, and the fraud proof is needed only when other validator thinks that the provided result is incorrect and want to challenge it. Compared to the ZKML and OPML, the main difference is that ZKML needs to generate a ZK proof, but we know that the cost of generating a ZK proof is extremely high, which limited the application of ZKML. Indeed, currently, ZKML can only handle some tiny AI model. But from the OPML perspective, since we can run the AI model in the native environment and then upload the result on-chain, and the throughput is needed only when other challenge is. Besides, the cost of generating a throughput is extremely low. Therefore, OPML can handle extremely large model. For example, currently with OPML, we can now bring the Stable Diffusion and Llama on-chain. From the AI perspective, there exists an AI Moore's law. That is, every year, the model size will increase by tens. And since OpenML can execute it in a nearly native environment, and thus OpenML can catch up with the model growth and bring the latest large model on-chain. Okay, after introducing the background, we are now going to look deep into the OPML architecture. There are three important components in OPML. That is the throughput virtual machine, FPVM, ML engine, and the dispute GAN. For the throughput virtual machine, given a stateless program and its input, the throughput virtual machine can trace any instruction step and prove it on the layer 1 blockchain. As for the machine learning engine, we have implemented a lightweight framework for the machine learning, that is MLGo. And for the interactive dispute GAN, which will help to locate a dispute down into a single instruction, and then we can resolve this dispute. Sorry. And then we can resolve these disputes using on-chain throughput virtual machine. And the OPML process goes as follows. There exists a requester, which will first send an AI inference request on-chain. And then one of the OPML nodes will serve as the submitter and then run the AI inference in his native environment using our ML engine. And then the submitter will upload the result on-chain. And optimistically, we'll consider that the submitted result is correct. And there will be a challenge period, during which other validator can check the result. And if one of the validator thinks that the provided result is incorrect, the verifier can indeed challenge the submitter and generate a throughput. And if the submitter is wrong, the result will be replaced by the verifier. And in the challenge period, other validator can also check and challenge it. As for the throughput virtual machine, the throughput virtual machine is for off-chain execution and on-chain arbitration. Specifically, you can consider that the throughput virtual machine is a state transition function, which will take the virtual machine image as a previous state as an input, and then execute one instruction, and then will output a new virtual machine image as a new state. Therefore, the trace of a program executed by the throughput virtual machine is indeed an order set of the virtual machine state. Besides, the virtual machine image will include the memory state, register states, and other VM states such as PC in the virtual machine. And the whole virtual machine image will be organized as a Merkle tree. And only the root of the Merkle tree will be uploaded to the blockchain. And the root of the Merkle tree will represent the virtual machine state. As for the machine learning engine, we have two core design principles of the ML engine. The first one is that we will separate the execution from the proving part, and this can guarantee the high efficiency of the machine learning engine. Another design principle is about the deterministic machine learning execution, which can guarantee if the AI result is consistent and verifiable. Under this design principle, we have implemented a lightweight framework for the machine learning, MLGo. As for the design principle of separate execution from proving, we have provided two kinds of implementation of the machine learning engine. The first one is for the native execution, where we will use multi-thread CPU and GPU to speed up the computation in machine learning, and which can guarantee a high-speed execution. Another one is for the throughput program. This one is needed only when someone starts challenge you, and you need to provide a throughput. In this implementation, we adopt a cross-compilation technology, where we will compile the ML computation into the virtual machine program instruction. This separation guarantees that the execution is fast, while the proving is based on the machine-independent code. As for the deterministic machine learning execution, we know that the native execution of the ML computation cannot guarantee the consistencies. This is because the parallel computations that involve floating point numbers often provide non-identical outcomes due to the rounding error. For example, the result of A plus B plus C is not equal to A plus the sum of B and C due to the running error if A, B, C are floating point. Besides, the hardware platform operating system can also affect the computing result of the floating point number. In our OPML engine, the consistency is guaranteed by two technologies. The first one is that we'll convert the floating point number into the fixed point. This is also known as the quantization technique in the ML in the machine learning. The second one is that we'll adopt the soft flow for the floating point calculation in the virtual machine. And if you are familiar with ZKML, you will know that ZKML cannot handle the floating point, and therefore ZKML always leads to accuracy loss. However, in OPML, with floating point support, OPML can achieve nearly zero accuracy loss compared to ZKML. As for the interactive dispute game, there are in the interactive dispute game, there are two parties, namely the challenger and the submitter. The challenger and the submitter will run the same machine learning program to identify who is wrong. They will indeed conduct a binary search algorithm to locate the dispute point. And once the dispute point is found, the one-step execution will be conducted in the Onchain virtual machine for arbitration. And here is a simple example to demonstrate the dispute game in the proper system. Assume that there is a submitter who will first submit a result on chain, but there exists another validator who thinks that the provided result is incorrect, and therefore the challenger will start a challenge with the submitter. And we'll assume that in this simple example, there are 100 instructions in the machine learning program. And initially, both the submitter and the challenger agree on the initial state as 0, but disagree with the final state as 100. And then the submitter and the challenger will start a binary search. They will first check the middle point, that is state 50. Assume that at this time, both the submitter and the challenger agree with the state 50. And this means that the dispute point must located in the state 50 to state 100. Again, the submitter and the challenger will check the middle point, state 75. Assume that at this time, they disagree with 75. And this means that the dispute point must located in the state 50 to state 75. And then the submitter and the challenger will continue and will start a binary search again. And finally, they will find a state where both the submitter and the challenger agree on, that is state Si, but disagree with the next state Si plus 1. At this time, the state Si will be sent to the on-chain virtual machine for arbitration. And if the output state Si plus 1 does not match the submitter state, which means that the result provided by the submitter is incorrect, and the challenger's result will be considered to be correct. And this result will also waiting for other validator to check it. As for the on-chain arbitration, the on-chain virtual machine will take the previous state Si as the input and conduct one-step execution to output the next state Si plus 1. Since the on-chain virtual machine only execute one instruction, the size of the data that needs to access is only 01. Therefore, we can add the necessary data to on-chain virtual machine by providing a Merkle pass. However, the current proper system has its own limitations, which make it impractical to support very large machine learning programs. The first limitation is that the current proper system has a very low execution efficiency. This is because in the current proper system adopted by the automated rollup, all the computation must be executed within the virtual machine. But the virtual machine can only be executed in a single-thread CPU. Therefore, it has very low execution efficiency. Another limitation is that the virtual machine only has limited memory. For example, the MIPS virtual machine can only support a small 4 GB memory. This limitation makes the current virtual systems impractical to support large machine learning programs. To overcome this limitation, we have proposed a novel multi-phase throughput system. There are two design principles in our multi-phase throughput system. The first one is the simulative execution, which can help to achieve a high execution efficiency. Another one is the lazy loading design, which can resolve the virtual machine memory limitation. In the simulative execution, with multi-phase design, we decompose the dispute game into multiple phases and conduct the computation in the virtual machine only in the final phase. For other phase, we executed the computational heavy part as a host function, and which can be conducted in a native environment. Compared to the current throughput system adopted by the optimistic rollup, the throughput system in OPML is much more efficiency. This is because instead of running the whole program in the single-thread virtual machine, we can now run in the multi-thread CPU or GPU or even using TPU to speed it up. Therefore, we can achieve more than 1,000 acceleration in our execution. As for the lazy loading design, the key idea is that we do not need to load all the data into the virtual machine memory at once, but we can only keep the keep that can identify the data item. When a virtual machine needs to accept a specific data item, the virtual machine can use its keep to fetch it from the external source and then load it into the memory. Also, when the data is not needed, we can swap it up. With this lazy loading design, we can now run a 26 GB large language model in a virtual machine with only 4 GB memory. Generally speaking, with our proposed novel multi-phase throughput system, we can achieve high execution efficiency with simulative execution and also achieve unlimited memory in the throughput virtual machine with our lazy loading design. And we are now able to run OPML with a 7 billion llama, whose model size is around 26 GB on a common PC, even without GPU. And now we will summarize the comparison between of OPML and ZKML. And first of all, ZKML and OPML adopt a totally different proving system. ZKML using zero knowledge proof to guarantee its correctness, but OPML using the throughput system. Because of the cost of generating a zero knowledge proof is extremely high, ZKML can only handle some small model. Compared to the zero knowledge proof, the cost of generating a throughput is extremely low, and we have already proposed a high-performance multi-phase throughput systems. And therefore, OPML can indeed handle extremely large AI model. And as for the hardware requirement, ZKML needs a very large memory for the ZK circuit, but OPML is much more friendly. And OPML can run on any PC with CPU or GPU. Therefore, the service cost for ZKML is extremely high, while OPML is much more lower. But OPML has a problem of the finality, which is also the problem of the optimistic rollup. OPML needs to delay for a challenge period, but ZKML can achieve instant finality when a zero knowledge proof is generated. From the security perspective, we know that ZKML is guaranteed by cryptographic techniques using zero knowledge proof, but OPML execute using throughput and throughput is secured by the incentive mechanism and game theory. Specifically, OPML has great advantages of its performance. OPML can provide machine learning service with low cost and high efficiency compared to ZKML, and the requirement for OPML is very low. And we have mentioned that we are now able to run OPML with a large language model on a common PC. But ZKML will take around 80 minutes to generate the ZK proof for a 1 million parameter small model on a server with 500 GB RAM. Therefore, currently, ZKML can only handle some small model, but OPML can handle nearly all the AI model. From the security perspective, ZKML can achieve cryptographic security, and OPML can achieve economic security under the antitrust assumption. Here, I am going to introduce the antitrust assumption. The antitrust assumption means that the OPML can maintain the security even when there is only one honest validator. Indeed, the security model of OPML and ZKML is quite similar to that of the optimistic rollup and the ZK rollup. Besides, I want to highlight that the OPML can achieve much higher security level compared to the existing Oracle protocol, which can only achieve security under the majority trust assumption. We have provided some mathematical calculation in our white paper, and this figure shows that the antitrust system can indeed achieve much higher security level compared to the majority trust system. And as for the finality, we can define the finalized point of ZKML and OPML as follows. The finality of ZKML is defined as the time that the ZK proof of the machine learning inference is generated and verified. And the finality of OPML can be defined as the time when the challenge period of the machine learning inference had ended. And we know that generating a zero-knowledge proof for a large model will take extremely long time. Therefore, when the model size is large, OPML can achieve the finality even faster than the ZKML, while ZKML is still generating the ZK proof. One of the optimization for the OPML is to shorten the challenge period so that we can achieve faster finality. The challenge period is related to the execution time in the virtual machine and the number of interactions in the dispute game. Our novel multi-phase throughput protocol can help to greatly shorten the execution time in the virtual machine. Besides, we can adopt the multi-step ZK throughput and multi-step challenge points to reduce the number of interactions in the dispute game. For the multi-step ZK throughput, assume that there is a ZK VM which can generate the ZK throughput for M step. And then with the ZK VM, the number of interactions can be reduced from O log n to O log n over M. Besides, we can also provide multiple checkpoints instead of only one checkpoint in our previous demo. For example, we can provide a K checkpoint in the dispute game. At this time, we can further reduce the interaction numbers from log 2 to log K plus 1. With these two techniques, we can greatly speed up the finality of the OPML, and it is possible to achieve almost instant finality. After introducing the OPML, we may find that in OPML, everything else needs to be public for the verification. So the problem is that whether it is possible or how to preserve the improved privacy or the model privacy in OPML. To answer these questions, we have released another research paper named Onchain, Optimistic Privacy-Preserving AI on Blockchain. The key idea of Onchain is that instead of running the whole model in OPML, also we don't want to run the whole model into the ZKML. In Onchain, we can run part of the model in the ZK, but the remaining part is in the OP. In this way, we can guarantee the improved privacy and the model privacy. For example, to achieve the improved privacy, we can we can left the first several layer in ZK part, while the remaining layers in the OP part. While this approach may not achieve fully ZK level privacy, but it is possible to ensure a secure and non-reversible of the user's input. As for the model privacy, although it is impossible to run the whole model in the ZKML, we can keep the privacy of part of the model. Take the fine-tuning model as an example. LoRa is a popular fine-tuning framework. We can keep the fine-tuning part in the ZK, while the remaining part is still in OPML. In this way, we can guarantee the model privacy of the fine-tuning part. Therefore, the servers can provide ML inference service without making its fine-tuning model public and open source. Here is the performance of Onchain. Since in Onchain, we only need to keep part of the model into the ZK, we can greatly reduce the ZKML cost. For example, the cost of Onchain is only 20% of running the whole model in the ZKML. Therefore, Onchain is the best practice for preserving privacy and also achieving high performance. With OPML and Onchain, we implement the first on-chain AI Oracle, OAO. With OAO, people can use AI model result on-chain. Currently, we have supported Stable Diffusion and Llama 2 in OAO. If you are interested in on-chain AI Oracle, don't hesitate to have a try. The architecture of OAO is as follows. I'm not going to cover the detail. If you are interested in it, you can visit our GitHub repo. In OAO, the user's contract can initiate the AI request by calling OAO, and OAO will publish this request to OPML node for the execution, and then OAO will return the AI result back to the user contract. With OPML and OAO, we can unlock many potential on-chain AI applications, and indeed we believe the future of on-chain AI is optimistic. For example, with on-chain AI, we can design an intelligent AMM, where the on-chain AI can improve the liquidity and the profit of the market maker. Besides, we can sell the AIGC NFT, and we can even generate a smart contract on-chain as an intent engine. Besides, on-chain AI can also help to identify malicious transactions and accounts. And then we can also set up a decentralized AI marketplace. One potential application of the on-chain AI is the IMO, initial model offering. IMO can indeed tokenize AI models. With the token for IMO, the open source AI organization can conduct fundraising for the ongoing development of AI models. Besides, it can also motivate the open source AI contributor to this open source project. The IMO process goes as follows. The AI model first will perform IMO and then release IMO token, and then anyone can buy the IMO token to own their share of the AI model. And the holder of the IMO token can earn the revenue of that IMO AI model. Generally speaking, with IMO, the open source project can get fundraised, and the token holder can also get the corresponding revenue. Yeah, that's all. Thank you.
And thank you very much for this. presentation. It's very insightful. So before we go into the question and answering section of this presentation, can you I mean usually we'll ask this, so can you tell us a little bit about yourself and how you have come to join the Web3 and also the OPML scene? Can you tell us a bit about yourself? Yeah.
Yeah, sure. And you can call me Conway. And indeed, I'm a researcher in both AI and crypto. I also do. I have tried to build and train some large language model the, in my previous work. And also very interested in blockchains. And I indeed a blockchain developer first. So when coming to the on-chain AI, we start thinking about whether it is possible to bring the AI on-chain. And then I explore some projects. I find that most of the projects will use the ZKML to bring the AI on-chain. But as we know that their knowledge proof is not efficiency enough. ZKML can only handle some teeny model. So I'm wondering that whether there is this another proof scheme that is much more efficiency. Therefore, we can bring some large model on chain. And then with this question in mind, I also looking for some AI, some blockchain project. And I find that in the rollup system, there are two types of rollup, ZK rollup and OPL rollup. But in the AI part, people are only focusing on ZKML. So I'm wondering that whether it is possible to build an OPML, like an OP rollup system. And this is the idea that why I propose OPML. And I try it, and I find it is more efficiency than ZKML. And I believe if you want to bring some large model on chain, OPML may be your only choices, at least currently.
Oh, thank you, thank you. Yeah, I mean, it's really interesting how OPML has came to be according to you, which is yeah, it's the response, I believe, to essentially what ZKML can get to provide. Out of curiosity as well, so for you personally, what's your favorite models that's recently released? So you mentioned you worked on LLM before. Any favorite models that you really like favorite ML models that you really like?
Well, uh, indeed, I like Chinese models that's Pangu, developed by Huawei. And
Oh,
I
okay.
am also one of the contributors of Pangu, indeed.
Oh,
And for other
it's a
open
large
source,
language model as well.
yes,
Yeah.
it is a large language model so
Mhm.
developed by Huawei.
Oh,
And
okay.
for other open source model, I really like Llama. It is small but powerful. And
Mhm.
indeed, in OPML, the first large model I bring it on train is Llama. And now you can use our OAO to bring the Llama result on chain.
Oh, great. That sounds interesting. Yeah. Thank you for sharing about it. So now I will open the floor for anyone in the audience to ask any questions. So yeah, feel free to open your mic or even type in the chat. While we are waiting for our audience to ask some questions, I'll start off
Yeah,
with one.
yeah, I
I
have question.
yeah, go for it.
Hello?
Uh, yeah, ZK, you can go for it.
Yeah.
Hello. Yeah, can you guys hear me?
Yep.
Yes.
Oh yeah. Nice presentation, Conway. I'm still not really understand how any trust assumption works and how it makes sure that there's a way there's a way as this some honest note to challenge the yeah to challenge the fraud proof basically.
Yeah. Let me share the slides. And so I'm familiar with optimistic rollup. Indeed, OPML works like an optimistic rollup. And there will be one submitter who will submit the result on chain and optimistically will consider that the provided result is correct. And any node in our OPML network can verify the result. And if the node thinks that provided result is incorrect, they can challenge it. And the proof system can guarantee that if the submitter is wrong, you can definitely successfully challenge it. And this is the reason why that we have said OPML can achieve security under the antitrust assumption. That is, we only require one node in our OPML network that is honest. Then we can guarantee the provided result must be correct.
All right. Thank you. But I'm still curious, like uh how you guys make sure that there are always nodes up to challenge, because I believe to check before making a challenge they have to run the computation again, which in ML case is quite computational heavy. So
Yes,
how you guys make sure that there's always some nodes that to run this, especially in a very large language model that requires very heavy computational power? Like,
yes.
what's the incentive to keep them running this kind of nodes?
Yeah, you asked a very interesting questions. Indeed, this is known as the verified dilemma. This is because the verifier in our nodes may be lazy. They won't check the result. They will not like to run the AI inference in their local again to check the result. So to handle this problem and to tackle the verifier dilemma, we have proposed attention challenge mechanisms. And this mechanism is released in our white paper. We have proved that with these mechanisms, since the validators in OPML nodes has incentive to check the result. And if the because we will reward them, and we have proved the next equivalent of this sorry, we have proved that the next equivalence is that all the submitter will provide the same result, and all the validator have the incentive to check it.
I see. Do they still get rewards in the case that the challenge is not valid? Like, let's say I felt that there's something wrong, but in the end, there's actually everything is fine, is correct. Do they still get any rewards?
Yes.
Or yeah, there's
Indeed,
nothing.
we have designed a similar mechanism. The problem you mentioned about also exists in the optimistic route system, because in the optimistic route system, the verifier may not have motivation to check the result. Indeed, we have designed a similar mechanism. For example, we proposed a mechanism like that's called attention challenge. That is, when the submitter submit a result, we require all the validators need to pay attention to the provided result, and he need to run their result of chain. And we will randomly select one of the validator to check whether they have do this verification. And if the verifier have do the verification, we will reward it. Otherwise, this verifier will be punished.
I see. So does that means that every nodes who wants to participate in this OPML network have to stake some tokens or crypto? Is that correct? In order to
Yeah,
get slash, yeah.
it depends. If you want to get some reward, because if you join as an OPML node, you can get some reward because you provide some ML service. And if you want to be the submitter, that is, you want to claim some reward for OPML and provide the result as OPML, then you need to stake some money. So in that case, if you provide a wrong result, you will be slashed. But as for the challenger, anyone can be a challenger, even as user. So if a submitter provided a wrong result and you are a user, you think the provided result is incorrect, you can also challenge it. With this mechanism, indeed, uh, indeed, as a user, you can always verify and challenge the result. Even there's no honest node in OPML, you can still guarantee that the provided result is correct.
I see. I remember seeing that you said the antitrust assumption is a lot better than multi-trust, something like that. Can I
Yes.
know what's the benefit of using the antitrust assumption compared to the normal trust assumption?
Well, uh, sorry, I'll find the slides. Yeah. Uh, we are comparing the antitrust assumption with the majority trust. For example, some Oracle protocols like Chainlink. The Chainlink need to guarantee the provided result, the result provided by Chainlink is correct. You need to guarantee that at least the majority node of the Chainlink is honest. But in OPML, we only require one honest node. And this is a reason why that OPML can achieve a higher security level. And we have do some mathematical calculation, and we can find that the antitrust assumption can always achieve a higher security level than the majority trust.
Okay, understand. Thank you. Yeah, I still have another question. Is in regards Oracle. How does Oracle comes into play in all this machine learning stuff? Especially like the one that you mentioned,
OAO,
OAO, right? Yeah.
yeah,
I still not understand what's OAO about.
yes. And indeed, this is a product we released recently. OAO is On-Chain AI Oracle. And indeed, the consensus of the OAO is using OPML. So it is totally different from other Oracle protocol. So if you want to, here's the OAO workflow. So if you want to initiate an AI inference, you can initiate an AI request using OAO functions. And then the OAO function will emit an event and publish this request to OPML nodes. And we have also mentioned that the OPML is running under the antitrust assumption. There will be many OPML nodes. And then one of the OPML node will serve as the submitter and who will submit the result on chain. And other OPML node will serve as the validator. They will check the result, and if the result is incorrect, they will challenge it. With the OPML process, the result will be sent back and upload to the OAO, and the OAO will invoke the callback function in the user's contract. In that way, you can use OAO in your smart contract. Therefore, you can accept so many AI models. For example, Llama, you can use directly using OAO to use Llama in your smart contract.
I see. Can you give me one example of using AI Oracle instead of using normal Oracle? Like let's say if I just require price feed, I believe
Yeah.
normal
Uh,
Oracle should available to do the job already. So what's the case of using a AI Oracle?
well, when you want to bring the AI result on chain, for example, currently it is impossible for you to use a Llama or using a stable diffusion on chain. But with OAO, we currently support stable diffusion and Llama. You can click this link, and we have provided a demo on it. Uh, for example, we are not supporting the stable diffusion in OAO. Therefore, you can mint a AIGC NFT using OAO stable diffusion to generate a pictures, and then we can mint it as a NFT. Also, for example, for the Llama, we have open source a repo. We will use the OAO Llama as the intent engine. So people will only interact with like people can interact with the smart contract like I want to send for 10 ETH. Then he can just write this text and then send to the on-chain AI Oracle. The on-chain AI the Llama will handle this request, and then we can generate a transaction for the user to conduct the transfer, the token transfer.
I see. Thanks for answering all my questions.
Yeah, thank you.
Thank you. So there's someone in the chat called Zhang. He's asking what are, as he's saying, what interesting topic, what are the data that you need to create fork proof and where do you store them?
Yes. Indeed, this is a problem about the DA for OPML. And currently, both the input and the output of the AI model, for example, Llama, is stored on chain because the input and the output is not so large. And to create a throughput, we need the user input, model, and also provide the output. We only need these three components. And the input and output will be stored on chain. And as for the AI model, because in OPML, we require that all the AI model is open source. So we will not solve the AI model on chain, of course. The Llama is very big. So we will only use the open source model that is available on the
Sorry, yeah. Please continue. I think I might need to actually set the room
There's so
settings
many
to something
random
strict.
people
Yeah.
coming in.
Yeah.
yeah.
I think that's insane. Yeah, continue, yeah.
Yeah.
Can
So
we
any other questions?
do have some questions. Sorry, give me a moment. I really need to see if I can set this. Oh yeah, YH Lai is asking, do you provide API or SDK?
Yeah, OPML is open source, and I can send the repo to you in the chat box. Wait a moment.
Yeah, thank you.
Yeah, the
So
GitHub
someone,
repo. Send it. Sorry, go ahead.
okay, sorry. Yeah, yeah, the GitHub repo is there. Yeah, thank you very much. So I have a question regarding how essentially what's the some difference between ZKML and OPML. So in ZKML, basically the idea is to rely on the cryptographic security to essentially make sure that the computation is correct. And you run one very heavy computation, which is very limited right now, and it can be verified everywhere to know that your result is correct.
Yes.
However, OPML, right now, from what I understand, it requires essentially a network to have people have the verifier submit fraud proofs to ensure that the result is correct. Is that idea correct?
Yes, that's right. So OPML, we need a network, or say we need some validator to check the result. And if the result is incorrect, the validator will provide the fraud proof to correct it.
Got it. So, would there be a case in which OPML requires a lot more machine to maintain, in the sense that because you require a set of verifiers to check for fraud proofs, whereas in ZKML you require strong provers. So the weight of your computation becomes running the models instead of running the provers to prove the models. Is that a problem, right?
That's a good point. But we want to mention that indeed the cost of ZKML is at least thousands or tens of thousands over OPML. So in OPML, we can run in the native environment. And as for the trust assumption, we have made a simulation. Indeed, with 10 validator, we can achieve a very high security probability. So I think that the cost of OPML is low. And besides, since we need some validators of nodes in OPML, we can encourage people to join our OPML network, serve as a service, as a validators, and they can earn their revenue from OPML.
Great. Understood. Thank you. Great. Any more questions? The audience.
Yeah. Can we have the slides?
Yeah, I can share the slide later.
Thank you.
Do you have any test node now? Sorry, currently, the OpenML node is commissioned. In not allow other people to join our OpenML because our throughput is still in testing and auditing. And we will make it open source and permissionless later.
I see. Yeah. So given right now, OPML is a solution for resolving the issue where ZKML cannot resolve. That is it's very hard or very computationally expensive to run a proof on like a big model like ChatGPT or even Llama. When ZKML becomes mature enough that it can do such big computation with a relatively cheaper price, what's the plan of Aura or OAO? Would you switch over to use ZKML, or do you think at that time OPML still have its merits?
Well, that's a good question. We also consider the futures of ZKML, and currently we have do some work combining the ZKML and OPML. And because we know that the ZKML is very limited, it can only prove some small model. So one combination way is that we can participate the model into two parts. The one part is in ZKML, another part is in OPML. Currently, because for example, for the 7 billion llama, it is impossible for ZKML to prove it. ZKML can only provide a proof for for example, for the first 5 layers, and the remaining thousands layer must be run in OPML. And when the ZKML become much more efficiency, we believe that we can put more layer in the ZKML to guarantee its private input and guarantees its efficiency. And as for whether it is possible that ZKML will totally replace OPML, well, I think that may be too optimistic because I have a slide here. This is because the model size increased very, very, very fast, which means that unless we have proposed a very cheap ZKML algorithm, since otherwise, because OPML can be executed in the native environment, so unless ZKML can also achieve such performance, I think OPML is still the only way that can catch up with the model growth and bring the latest large model on chain.
Thank you. Yep, that sounds like that's good news, right? Because I think OPML definitely has its place in the ML world, and ZK, at least right now, it's very difficult to scale to like very huge models, and I think in the future it will still be expensive, right? Unless there's some new breakthrough. Yeah. I think that's any more questions? If not, then we can. Oh, yeah. There's questions in the comments. So it's asking about the local node in chat. If you can take a look at the chat.
Okay. Yeah. Currently, we do not publish currently we do not make a public and permissionless OPML network. So you cannot join our OAO currently, but we will make it permissionless later. But using our OPML repo, you can create your own OPML. You can run your own OPML node and create your OPML subnet. And currently, we do not involve any token in our repo, so you do not need to generate with any token or coins.
Sounds interesting. Yep, definitely gonna try that out. Any more questions? If not, I think we can end this session. Yep, I think that's all for now. Thank you very much, Conway,
thank you
for coming here and giving us a presentation on OPML. It's very insightful. Sorry for the disruption in the middle. I did not expect that.
That's okay.
But yeah, thank you very much. I'm gonna stop recording now. But for anyone who wants to ask question later, you feel free to. Let me just stop recording now. Yeah, thank you.